eigenvalues today, so this will be the end of chapter 5. And we'll talk about some equivalent conditions for diagonal matrices and what happens in the case of invariant subspaces for reals. And next time we'll start with inner products, which is in chapter 6. So one of the main nice forms of a linear transformation is a linear transformation which has a diagonal matrix. And by its very nature, of course, this is a property of a linear transformation in a basis, right? I can't even say what the matrix is without choosing a basis, so it sounds like it somehow depends on the basis. But the property F has a diagonal matrix for some basis of V. So here F is a linear transformation from V to itself. This property is a property of F which does not depend on the basis. This is a property of the linear transformation itself. And one of the things we want to get a handle on is how we can understand this property apart from just finding that basis and writing it down. So ways of equivalent, things which are equivalent to this notion. And then later on we'll get to the spectral theorem that tells you when a linear transformation, exactly when a linear transformation has a diagonal matrix for some basis. So the proposition that does this is the following. Okay, suppose a proposition that does this. Suppose F in lambda V has distinct eigenvalues lambda 1 up to lambda m. Now, we're not saying that it has dimension of V distinct eigenvalues. We're just saying however many eigenvalues it has, which are between, well, which has between 0 and dimension of V. That's what they are. That's just a list of the values. Then the following are equivalent. The following things are equivalent. The first is this one, this statement. F has a diagonal matrix with respect to some basis. And this is sort of believably independent, basis independent in the sense that I could write down a diagonal matrix. I could certainly do a change of basis that gives me a different diagonal matrix, like permuting the basis elements, for example, will give me a different diagonal matrix, but it's also diagonal. But this still has the word basis in it, right? It still seems like it's a basis, at least related concept. And we're going to make sort of increasingly less basis-related statements of this. V has a basis consisting of eigenvectors. Of F. So these are sort of almost the same thing as we've already discussed from the time we introduced eigenvectors and even from the time we introduced bases. Okay. Here's a statement that sounds a little bit less basis dependent, although it's essentially equivalent. One-dimensional. Well, it's exactly equivalent. There exists one-dimensional subspaces, U1 up to UM, one-dimensional subspaces U1 up to UM of V, each of which each of these subspaces is F invariant. And V is not just a sum, but a direct sum of these subspaces. And you remember there's a very tight relationship between the idea of a basis and the idea of a direct sum of one-dimensional subspaces. This is using that relationship. Now here's something that's even less sort of strictly less basis dependent, but turns out to be equivalent. So suppose I have this basis of eigenvectors. There's some amount of eigenvalues lambda 1 up to lambda m. This little m is smaller than the dimension of V. So by a pigeonhole principle, some of the eigenvectors are going to have to correspond to the same eigenvalue if m is strictly less than the dimension. If m is equal to the dimension, there's dimension V, distinct eigenvalues. It's kind of the nicest possible situation. But if m is strictly less, some eigenvalues will have a positive dimensional eigenspace, or be a larger than one-dimensional eigenspace, right? And if we sum all those up, so if we group the eigenvectors by that, we get an expression like this. V is the null space of f minus lambda 1 times the identity. That's the eigenspace associated with lambda 1. Direct sum all the different null spaces of each eigenvalue. Okay, so this is strictly less basis dependent in the sense that by grouping the basis vectors according to which the eigenvectors, which are also basis vectors, according to which eigenvalue they correspond to, I'm able to forget the basis structure of these component spaces, right? I don't really care about this space other than to say it is a component vector space and it's the eigenspace, but I don't need to worry about exactly what basis I've chosen inside that space. So that's sort of a less basis dependent notion, though it still has this decomposition structure. And finally, we can do it by just talking about dimensions themselves in this expression. So the dimension of V is equal to the dimension of the null space of f minus lambda I V plus the dimension of the null space of f minus lambda m I V. And I want to emphasize that not on this list, so not equivalent to statements A through E, is that m equals to mv, that all the eigenvalues are distinct, right? This is a sufficient but not necessary condition for these things to hold, these equivalent properties to hold. Okay, so let's prove this. And a lot of this proof will be, since it's a bunch of equivalent statements, some of the things will be harder than others. A lot of them will be fairly easy. So A and B, this is almost by definition, again, from the beginning, the way we introduce these things. To have a diagonal matrix means that each input vector, it can be expressed as a linear combination of just the same vector, but that's the same as saying that that's an eigenvector. That's what it means to be diagonal. So suppose that we have B, and we want to get to C. So we have that it has a basis of eigenvectors, and we want to talk about one-dimensional subspaces. Again, this is already also almost tautological. The subspaces that we use are just the spans of the eigenvectors. Then saying that V decomposes into a direct sum of one-dimensional spaces, each of which is the span of a vector, is the same as saying that that list of vectors is a basis. Because if V can be written uniquely as such a sum, U1 up to U, well, here this actually would be N, right? This is N, really? Well, M equals N in that case. No, I'm sorry. Yeah, it's N. It has to be N because it's one-dimensional. The direct sum says that there's only one way to write it this way, but each ui is just equal to a coefficient times this some vector. So it's the same to say that this has unique decomposition or that there's a unique linear combination in terms of the basis elements. It just says, I have to scale V1 up to Vn. I have to scale each one, and there's only one choice that makes that true. Okay, so for continuing B goes to D, So B, we have a basis, an eigenbasis, a basis consisting of eigenvectors of F. And we'd like to show D this more complicated statement that says that V splits up into a direct sum of null spaces, each of which may be larger than one dimensional. And for this, we just use this idea of grouping. So, each V is a linear combination of elements of eigenvectors, because these are the basis, since we have a basis consisting of eigenvectors, and we can group the eigenvectors V1, V2, which are also basis elements, by which lambda they go to. Maybe these both go to lambda 1, this one goes, so lots of things can happen, right? So we just group those up and take their spans of all of the vectors which belong to this eigenvalue, and that gives us this statement. Well, at least that gives us part of the statement. It tells us that V is a sum from j equals 1 to m of these null spaces. So it doesn't quite tell us that that representation is unique, but it certainly tells us that I can write it that way, right? To prove that it's a direct sum, I have to show that the representation remains unique even after I've done this grouping. So there's no freedom to move around, say, inside the null spaces. So suppose we could write zero as a sum I equals 1 to m of ui, with ui in null f minus lambda I times the identity. Well, we know that these ui, each of which lies in a different null space, have to be linearly independent of each other. Why is that? Theorem we proved a little while ago. Not today, but another day. Why are the ui independent? Well, they're independent because they correspond to distinct eigenvalues. And there's a theorem that we proved that says that that means they're independent. So since they're independent, then and they sum to 0, they must be all 0. Okay, so that means it's a direct sum. So that D implies E was part of one of the exercises we did when we were talking about direct sums. That doesn't have to depend on the particular structure of the problem. In the other direction, or suppose that I have that E is true, so that I have that the dimension of the sum, the dimension of the space is equal to the sum of the dimensions. And choose a basis for each null space, for each eigenspace, lambda j, I v. And then put those, just concatenate those together to form a big list. A big list of vectors. That list of vectors, because the dimension the sum works out, that list will have to be length n. And it'll be like the vectors that span the first eigenspace associated to lambda 1, the vectors that span the second eigenspace, there's 4 of those, etc. So then this list will be length n, so in order to show that it's a basis, it suffices to show that the list is linearly independent. Because a linearly independent list of the appropriate length has to be a basis. So suppose that ui is the sum of the ai vi, I equals 1 to n, equals 0. So suppose we've chosen some linear combination of these vectors, which gives us 0 with not all ai, or we want to prove that all of the ai's have to be 0. I'm going to call this u, even though I know it's 0, for a reason that will become clear in a second, so that I could talk about parts of u. Okay, so u, let's call uj the sum of the akvk's, where the vk are in the null space of f minus lambda j identity of v. So in other words, this is some big linear combination, and I want to take this combination and ignore all the coefficients except those that correspond to a particular eigenspace, vectors in a particular eigenspace, and then this uj will be in that eigenspace. Right? Null f minus lambda j IV. It's kind of the part of u that comes from that null space. You can think about it that way. Or the blocks in the sum. These uj are also eigenvectors. They're sums of eigenvectors, linear combinations of eigenvectors, all of which have the same eigenvalue. And they're independent if they're non-zero. Because they correspond to distinct eigenvalues. But their sum, the sum of all these uj's, u1 is 0, and they're independent, so it must be that they're all 0. Well, they're independent or they're 0, so they must be all 0. Okay, so that means that 0 is equal to uj is equal to the sum akvk with vk in the null space of f minus lambda times the identity lambda j times the identity of v. But these vk's were already a basis, in particular independent. So this is a linear combination of independent vectors which equals 0, so all the ak's are 0. And so the big list here, the list of concatenated list of the basis of all the null spaces is linearly independent and therefore a basis. Yeah. So the last topic in this chapter, before we move on to the next chapter, which we'll do next time, is what happens when we go to the real case. So we're mostly talking about either the complex case or the case which could be either. And there's some special things that happen for real vector spaces that we want to discuss now. In particular, the structure of their invariant subspaces. So we know that if V is a complex vector space, every operator has an eigenvalue. And we know that that's false for vector spaces over reals. And the example is the plane, just rotation in the plane moves every vector except the zero vector. There's no eigenvectors there. That's easy to see. And when we prove that every linear operator on a complex vector space has a eigenvalue, what we did is we used the factorization idea, right? We raised f to a bunch of powers, applied it to a single vector, got a list of too many vectors to be independent, wrote them as linear, zero is a linear combination of them because they're dependent, factored that, treated that linear combination as a polynomial. Because it's over C, it factors into linear terms. We look at the composition of linear terms and we say one of these things has to be responsible for killing the vector, and therefore that one is not injective, therefore there's an eigenvalue. Okay? If you remember from the chapter on polynomials, when we go to polynomials, or when we go to the real, we no longer have the fact that every polynomial can be factored into linear terms. We have to have linear terms and quadratic terms. That was the equivalent thing, because we can't solve the quadratic equation over R. And so the hope, because of that, or the idea because of that, is if we apply that same logic, we'll get this sort of rotation phenomenon of a two-dimensional invariant subspace, which has no eigenvalues, is kind of the worst thing that can happen. That's the theorem, and that explains the strategy we're going to take to prove it. So every operator on a finite dimensional non-zero real vector space has an invariant subspace, which is F invariant. And it has such an invariant subspace has dimension 1 or 2. So 1 if it's an honest eigenvalue, and 2 if it's one of these sort of copies of something that moves every vector but at least fixes the space. And we want to proceed exactly as we did for the complex case. It's just we'll get a different answer because the factorization theorem is different. Okay, so we have a real vector space of positive dimension, and we have a linear operator on that space, and we just take any vector v in V which is not the zero vector. Take a non-zero vector in the space. And now we're going to construct a list that's too long, a list of vectors just from those ingredients that's too long to be independent. And that's f to the 0, which is the identity applied to V, so otherwise known as V. F applied to V, f squared applied to V, all the way up to f to the n applied to V. That's a list of length n plus 1 vectors in an n-dimensional space. And so it must be dependent. Since it's dependent, there exists a linear combination of these vectors, which I can write this way. Sum from I equals 0 up to n, a sub I f to the I, applied to V, with not all the coefficients 0. Right? That's what it means to be dependent. So forgetting about V and the fact that this is a linear operator, we argued already that there's an isomorphism between this ring and the ring of polynomials. So we can think about this as the polynomial, or we can think for a moment at least about the polynomial which has the same coefficients, and it's just a polynomial where this takes values in C instead of taking values as a linear operator. Now we apply the theorem, which is the real version of the real field version of the fundamental theorem of algebra, which says that this polynomial factors as some constant, which is not 0 unless it's the 0 polynomial, times a bunch of linear factors, which have suggestive names for their constants. Those linear factors are going to correspond to the eigenvalues, those lambdas. And those get multiplied by quadratic factors, x squared plus alpha 1x plus beta 1, x squared plus alpha big M x plus beta big M. So this time we only get linear and quadratic factors. And all the things appearing here, alpha, C, beta, R and R, and lambda I. Okay. So then, thinking back in terms of applying this to operators instead, what we get is that this guy, the operator that we were interested in, applied to V, which we know is equal to 0. This is kind of a sum, scalar multiples, compositions of linear operators, of a linear operator, scalar multiples, and I sum it. So I'm using sort of the vector space structure as well as the compositional structure here. But this is a big sum. That big sum is equal to a long composition of many linear operators. Well, the scalar linear operator times f minus lambda times the identity, lambda 1 times the identity, up to f minus lambda little m times the identity. These are the operators that are linear operators in V, which correspond to the eigenvalues. And then I do the ones that correspond to these square things. Alpha 1f plus beta 1, and the beta is multiplied by the identity because we're times f squared plus alpha m f plus beta m identity. So these are all perfectly good definitions of operators. And then we want to make the same sort of argument. So on the left-hand side, we have a sum of many linear operators. On the right-hand side, we have something which is just simply a composition. And it's this theorem about polynomials that allows us to know that we can make such an equality. I forgot a V here at the end, right? So now we take this V. We know that when we feed it through this long chain of linear operators, the output at the end will be 0. And there are only finitely many of them. And we know that at some point, one of these linear operators has to take something at its input and send it to 0 for that to be true. Right? So it could be that these are all don't send anything to 0. They're all injective. And then when I hit one of these operators sends it to 0, in which case one of these things has a null space, non-zero null space, in which case one of these things is the eigenvalue. And then we're done because we've shown it has a one-dimensional subspace. So if a f minus lambda j I v is not injective, have eigenvalue lambda j and a one-dimensional invariant subspace associated to any eigenvector, the span of any eigenvector of it, right? Of which there might be more than one. more than there might be, which may be a positive dimensional space 1 or higher, 2 or higher. But the other case that could happen is that one of these has a non-trivial null space. So one of these might be not injective. And what do we do then? So then, in other words, there exists some vector u, which you can think of as being the sum of the one intermediate thing. Like maybe I do this a bunch of times, and I get a u, and then this guy kills it. So there has to be some u in V such that u is not 0, and f squared u plus alpha j fu plus beta j u is equal to 0. And in that case, what we want to identify is the invariant subspace. Yeah.
What's that, between one-dimensional and subspace?
Invariant subspace. A one-dimensional exists. Which is the span of some eigenvector, non-zero eigenvector for lambda, this lambda j. Okay, so yeah. Question? So we have this fact. So we know that one of these quadratic factors is not injective, and we want to understand how to construct an invariant subspace from that fact. It was easy for this. You just pick some eigenvector of it. We want to show that it exists here. Or something in the kernel of this, rather. Something in the null space of this. Eigenvector of f. So the claim is that the answer is span of u, whatever this u was, that it's set to 0, and f times u. So the claim is that this is f invariant. And that's our two-dimensional f invariant subspace, which is promised by the theorem that I'm erasing right now. Okay, well, to prove that, we just have to say, well, take an arbitrary element. That's an arbitrary element of the span, a linear combination. And apply f. Then I get, well, I get, AFU plus BF squared u. This part is certainly in the span because it's a multiple of one of these vectors. And the key thing is to show that this vector f squared u can be represented in this space by u and fu. But that's because we know that f squared u plus alpha j fu plus beta j u, u equals 0. Right? That was, we had chosen u to be something that was killed by that quadratic factor. But that means that I can move fu to the other side minus beta j u. And so I can just substitute this in here. And therefore, f of this can be expressed as something in the span of u and f of u. So f of au plus bfu dfu equals afu plus b, and then this expression, minus alpha j fu minus beta ju, which is manifestly in this span. So before we prove the last theorem of the chapter, and we begin the next chapter, which will also use this idea, I want to go over this idea of projections. Direct sum and projections to part of the direct sum. One way to define project sum is to, a way that extends very nicely is to use this kind of a projection idea. So we define it in a different way, and we can prove that such things exist. So suppose V is the direct sum of U and W. That means for all V and V, there exists U and U. There exists a unique U and U. There exists a unique, well, a unique pair of U and U and W, such that V equals U plus W. There's only one way to write V as a sum of something in U and something in either lowercase, something in W. Now, because it is unique, if it was not unique, if this wasn't a direct sum, I could change this one a little bit and change that one a little bit and have a perfectly good representation, right? But because it's unique, I can define the following function, Puw of V, which is I write V as U plus W, and then I take the part which was in U, which was in the vector space U, right? This is in U, this is in W. So let's say the U part of it is you take V, you write it this way, and you take the part that was in U from the direct sum. In general, if I just write without the uniqueness, this won't be well defined. It won't be a function, but because it's unique, this is a function. And just as we did with some of the other functions that were defined in a similar way, you can prove that this is linear. Not just a function, but it's a linear transformation. You could think about it two ways. It's a linear transformation which sends a vector in V to another vector in V. U is in particular a vector in V. You could also think about it as a linear transformation which goes from V to U, because it always spits out something which is in U. So its range is contained in U. Think about it either way. So these are linear operators. Moreover, they satisfy a lot of nice properties. One is that P of U, W of V, if that equals V, that happens if and only if V is in U. In other words, this projection operator has a restriction to U, and on that restriction, it's just the identity of U. Yeah, another way of saying that is that this thing is PUW is idempotent. Idempotent is something. Idempotent is something. If I do it more than once, I get the same. It doesn't change the state of the thing anymore. Like if I unlock a door and I unlock it again, it's still unlocked. So that means that PUW squared, doing the operation of projection and doing it again, is the same as doing it once. Idempotent linear operator. I can think about this as how I express a direct sum, like how I compute these things. So when I just say there exists such a thing, it doesn't tell me how I get this. But once I've identified what these operators are, it must be that the direct sum decomposition can be expressed like PUW applied to V. That's the U part. Plus P, the other one, are WU, so the part which projects to U, applied to V. So that's another way of saying what the direct sum decomposition is. Or computing the direct sum if you figure out what these operators actually are. And other observations about projection operators. Is that, we already mentioned that the range of PUW is U. We can also say that PUW as a map from V to U is surjective. So it's not surjective as a map from V to V, but as a map from V to U, it's surjective, because if I take anything in U, plug it in over here, I just get it back. So I can always write any element by just using it to begin with. And they are nicely compatible in the sense that if I take the null space, the things that this projection operator sends to 0, I get exactly the other space in the direct sum. So there's a number of things you can prove with these, and we will prove a number of things with these, especially in the next section on inner products. Lots of applications of projections, but we'll look now for a moment at this theorem about, our last theorem about invariant subspaces for real operators, and that's that every operator on an odd dimensional real vector space has an eigenvalue. So you can maybe get a guess as to how this proof is going to go, right? I mean, the importance of being odd is that we know that there are other 1 or 2 dimensional things. And if I want to get an odd number by adding up 1s and 2s, there's going to have to be a 1 in there somewhere. And that 1 is sort of going to loosely correspond to the